Hi, and welcome to yet another exciting session of Gr10 Physical Sciences. Today we're looking at the last segment of our knowledge area, which is based on electricity and magnetism. We're going to look at electric circuits. Now that we have a finer understanding of the concept of electricity, which is current, potential difference, which we sometimes refer to as voltage, as well as resistance. Let's have a clear general overview exactly as to what is it that we want to achieve by the end of this session today. Right, without any waste of time, here is our flow chart for today. So we'll be looking also at current, which is a very key concept, which has to do with charge that is moving in a per unit time. And remember, current is it's I, which is the symbol there, which stands for current or current intensity, if you want to think of it that way. So we'd measure the current using an ammeter, because we're asking ourselves how much charge passes through a point in a given time. Hence, we connect it at a point. Okay, we connect it at a point. Right. So having understood that, it means that these ammeters or whatever instrument which we use to measure current is an ammeter. We connect it in series at a point. Right. We also have another very key concept, which is potential difference, which we sometimes shorten for PD, which is potential difference voltage. It has to do with energy transformation. Work is energy. We know that when work is done, energy is transferred from one form to another. This is per coulomb of charge. Right. So let's say, for example, we've got charges flowing through a conductor. What happens is that the cell or the battery provides a source of potential difference in terms of changing chemical energy, which is contained inside the battery, into electrical energy, where we have this current which is flowing. So the flow of current is a result of potential difference, or the EMF, which is this one is when the maximum energy that a cell or a source can supply when no current is flowing. So this has happened when there is no current flow, right? So this happens when there is no current flow. But then when we connect, or say we close the switch, then we have what is called the terminal potential difference. This is when there is current flowing in the circuit. Now it means there is energy conversion, or the cell is doing work now in the circuit. And it could be lighting a bulb that's transforming electrical energy to heat and light, right? And also we shall measure this potential difference in terms of energy transfer between 2 points, right? Between 2 points. Hence, we talk of a difference in terms of potential energy of a charge between 2 points. So the voltmeter becomes then the instrument in that regard, right? So if that's the instrument, we measure it in parallel. We always connect it in parallel, because suppose this is our light bulb. So to measure the potential difference across the light bulb, we'll always connect it in parallel, which is very important to say that it is between 2 points. So we may think of these light bulbs, the heaters, the speakers, as resistors, in the sense that they are involved directly in the transformation of electrical energy to other forms. So resistance is that quantity which has to do with the ratio of potential difference across a component and the current flowing across it. So we may connect it in series, meaning that there is one path for which current flows, or we may connect it in parallel to represent more than one alternative path in which current can flow. So in other words, this is what we're saying. So this is a typical parallel circuit. In this case, it means when current reaches that point, some of it goes in that direction, some of it goes in that direction. Hence, we talk of resistors in parallel. So in this case, we know that voltage will remain constant. We shall speak to that at a later stage. But then if we talk of equivalent resistance, we're talking about the combined resistance of resistors. It could be in series or it could be in parallel. So we talk of equivalent resistance. So if this is, let's say, 2, 3 ohms and 4 ohms, the equivalent resistance in this setup then will be 9 ohms. So we shall talk about the concept of equivalent resistance quite a lot in today's lesson. Right, let's look at a typical example. Before we look at the example, let's go over the very key concept in this section. Right, so resistance will be, in this case, R, okay, capital letter R, which has to do with energy transformation. So resistors can be connected in series, meaning that there is one path for current to flow, right? So if there's one path for current, it means all the charges that pass at point A will pass at point B, as long as there's one path. Hence, the equivalent resistance in a series circuit, we simply add. So this formula becomes very, very, very key as far as series a circuit is concerned. So current, as the flow of charges, remains constant in the sense that whatever current passes through the first resistor, it will also pass, they say this is R1 and this is R2. So the current or the charges that flow through these two resistors will be constant and equal, right? In this case, so if we place an ammeter before R1, it will measure the same current as the one that would connect, say, for argument, at this point. So the quantity of charge that passes through a point remains constant. So current is constant in a series circuit. However, when we talk about potential difference, which is our voltage, sometimes we abbreviate it with V. So it simply means that potential difference will be divided proportionally. It means that, say, for argument's sake, we've got, let's say, R1, okay, and then let's say we've got R2 still in a series arrangement. So if we connect a voltmeter across each one of them, and let's say they are of different magnitude of resistance, so that is V2. So what is going to happen here? The current remains constant. However, the voltage in this case is going to be divided. Let's say if R1 is greater magnitude of resistance than R2, it simply means that the V1 will have a higher reading of voltage compared to V2, because we're saying that when voltage is divided in a series circuit, it is divided proportionally. So it simply means that if as current remains constant, we're saying that the higher the magnitude of resistance, the greater the voltage across that particular resistor. However, when we add the resistance, it will give us the total resistance in terms of the terminal potential difference. Remember, the circuit or the cell is doing work in pushing these charges around the circuit. Right. Then we, on the contrary, here have resistors in parallel. So parallel means more than one path for current to flow. More than one path. More than one path for current to flow. We made a simple sketch earlier on. We said that if we're talking about a parallel combination of resistors, we have something of this sort, right? Okay. So if that's the case, it simply means that the current in this case is going to be divided. So some of the current goes in that direction, some of the current goes that direction. But what is very key about voltage in terms of a parallel circuit is that it remains constant. Only current is divided. In other words, let's make a simple example. Let's say, for argument's sake, we've got a resistor of 2 ohms. Okay, it is connected in parallel with another resistor, let's say of say 4 ohms, which is double, right? Okay. Now, what we've said is that as current is flowing, we would understand that more current will go to lesser resistance, to the resistor with lower resistance, and lesser current will go to the resistor with higher resistance. In other words, they are of inverse proportion as current is divided. But if we have, let's say, V2 here, and then let's say we've got our V1 there across, these two will be the same in the sense that we're saying potential difference is constant in a parallel, yet in a series circuit, current only remains constant. Right. Let's look at an example, maybe to just to give us an idea of what we're talking about. Now, consider the circuit. Circuit is closed. In this case, we've got our switch there. Then we've got the cell there, which is connected to 2 light bulbs. Remember, we use symbols to draw a circuit. You need to pay careful attention to that. So the switch is closed. In other words, the cell is doing work or is transmitting energy in terms of chemical to electrical as current flows. Remember, by convention, it flows from the positive terminal, okay, to the negative terminal. So also those symbols are very important. How would you connect the ammeter to measure the current through wire A? So the wire A, well, let's think of wire A as an electrical conductor, right? So wire A is an electrical conductor. Let's go back again and remind ourselves, what exactly is an electrical conductor? It is that kind of material that allows electric charge to pass through it. Having said that, so we want to connect an ammeter, and we know that an ammeter, it measures current. And we know that current is quantity of charge that passes through a point in a given time. So the conceptual understanding of that becomes very, very important at this stage. So if we are to connect an ammeter, all right, let me remove that. So we could basically put the ammeter at a point, and then we show the sign there. It means all the current will pass through that ammeter, okay? And then it goes through to light bulb 1, light bulb 2, across through the switch and back to the cell. So in other words, it's very important to say that an ammeter is always connected in series. Always. You can underline that. Always connected in series. Very, very important. So in series is another way of saying at a point, right? So it's always connected at a point, right? Let's check the other problem again. Then the same diagram, on the same diagram, we are told that the diagram, this still contains the same cells, 1 cell and 2 light bulbs that are connected in series. We were told that the current that was going through current at A, so current here at A, right, is equals to 0.6 amperes. So the SI unit of current is the ampere. Very, very important. In other words, it says, if you can think of it in terms of the concept, it says 0.6 coulombs of charge pass through point A per second. That's what it means. So that and that exactly one and the same quantity. So what is the current at point C? But the key thing here is that this is a series circuit. And in a series circuit, there is only one path for current to flow. Now, that simply means that, again, the current remains constant, okay? Current remains constant. So we're saying, by all means, that whatever current passes through bulb 1 will also pass through bulb 2. Very, very important. So it's what? So the moment this question says what, there's no need for you to calculate. In other words, at the best of times, it will be 1 mark. Look out for that as well. Very, very important. Right. Now, in this very same diagram, we are told that the same circuit, it says how much current. So we want the quantity of current that passed a point C if the circuit was closed for 2 minutes. So what do we know? We already know conceptually that I is equals to quantity of charge that passes through a point per unit time or per second. So if we are given the current, in this case, the current that we were given was 0.6 amperes, okay, which passes through per second, right? So in other words, we're saying that 0.6 coulomb per second of charge, 0.6 coulombs of charge per second passes through that per second. So now, in 2 minutes, we have to change the 2 minutes to the SI unit because we're talking time. So it will be 2 multiplied by 60, which is equals to 120 seconds. What did we agree on? We agreed that per second, there's 0.6 coulombs of charge passing through a point. Now, in 120 seconds, so it means the quantity of current that will pass through in that time. It simply means that if we want the magnitude of current or the quantity of charge that will pass through, it will be 0.6 multiplied by 120. So I think it's important there to highlight that again. So the time is 120, okay, 120, right? And then if per second we've got 0.6, so we just multiply that by 120 to get the magnitude of current, right? So if we go to the calculator, we know that 120 is the time, okay, multiplied by 0.6, okay, which is 72, right? Okay, which is equal to 72 amperes of current passes through that in 2 minutes. In other words, per second, we've got 0.6 coulomb of charge passing through. That's charge in coulombs every second. Now we want to know in 120 what will be the current, right? And then that said, our example continues, right? How would you connect a voltmeter between points A and B? So between A and B, we know that a voltmeter is always connected across. It's between 2 points. So we are measuring the quantity of energy or the amount of work done between the 2 points there. Very, very important, right? So potential difference is between 2 points. Very, very key. Right. That said, it will be very important also for us to understand that as far as voltage is concerned, we're talking about how much energy or work is done between 2 points, which justifies why we connect it in parallel. Right. That said, we shall take a short breather, then we shall look at more examples and attempt a couple of questions. See you after the break. Welcome back after the short break. We shall continue with our scenario that we discussed in terms of the key concept, which is current, potential difference, and resistance, before we go into the finer detail of the circuits and the calculations. Because what remains very important is the conceptual understanding of these three very important physical quantities. That is current, resistance, as well as potential difference. So now the battery here is marked 3 volts, right? The voltage across AB was found to be 1.8 volts. So if the voltage across AB is the same as across this light bulb one, let's call that V1 for argument's sake, right? Okay, we found it to be 1.8 volts, right? And then if you go further, it says what is the voltage across CD or DC. So if we have, let's say, another voltmeter, let's call it V2 for argument's sake, right? So we know this is a series circuit, but what do we know about a series circuit? We know that voltage is divided, okay? Voltage is divided. However, when it's divided, it's done proportionally, right? Proportionally. So in other words, what we mean, we're saying that the higher the resistance of the light bulb, the greater the work done across it per coulomb of charge. Right. So that said, we understand that if this is the 3 volts is the total voltage. Let's call it V total in this case. Right. It's connected across the source. Right. So in other words, what are we saying? We're saying that V total is equals to V1 plus V2, meaning that the total voltage is divided in the circuit, right? So what are we saying? If we've got our V total, which is equals to V1 plus V2, we are simply saying that the 3 volts is equals to our V1, which is 1.8, plus our unknown V2. So this is a simple linear equation. So if we can transpose and do our maths, it takes us to V2 is equals to 3 minus 1.8. Okay, just to verify that, right? 3 minus 1.8. It gives us exactly 1.2, right? So 1.2 is volts is our voltage for V2. Then it says here, explain why VA is different to V across AB. Let's call this V1, okay? This is our V1, and then this is our V2. Why are they different? It simply means that, remember, the higher the resistance, okay, the higher the resistance in a series circuit, the greater the voltage, okay? So these two are directly proportional. So in other words, V and R are directly proportional, right? That said, okay, the same example continues and says here, it talks about how will the brightness. Now we need to get something clear here. When we talk about brightness, brightness speaks to the quantity of current. Brightness implies current, right? So the higher the current, the greater the brightness. But this is a typical series circuit, okay? This is a typical series circuit. So in any series circuit, we know that current remains constant. So in a series circuit, current is constant, right? So what that simply means by implication is that whatever current passes through bulb 1, it will also pass through bulb 2. So for that reason, these two will have the same brightness in the sense that there's the same current, right? Same brightness. So the reason why we observe that is because this is indeed a typical series circuit in which current remains constant. The only quantity that is divided in this case will be your voltage, right, which is divided proportionally, okay? That said, now it's time for us to look at a couple of questions, which I'm going to give you a couple of minutes to try, just to get through the questions so that we have a clear understanding as to where we're going with this. It says study the circuit below in this case, right, and answer the questions that follow. We've got the EMF there, which is 3 volts. Right, now we've got also A1, which is our ammeter, A2, A3, and A4. Now, just to give you a chance to respond to the first question, is this a series or a parallel circuit? Briefly explain your answer. I'll give you a minute to try that, and then maybe we can do a feedback and highlight one or two key things before we delve deeper into the calculations regarding this contextual problem. Right, let's go for it. Right, guys, hopefully you've looked quickly at this question. Now the idea is to classify this as either a series or a parallel circuit. But the key idea between the two types of connections is that one, which is the series circuit, has got a single path in which current flows, whereas as far as a parallel circuit, there is more than one path or direction in which current can flow as far as the connection is concerned. So because when current reaches this part, right, some of the current goes to that, some goes to that one, some goes to that. So current is divided. So in this case, because current is divided, this is a parallel circuit. Okay, there is more than one path. There is more than one path. for current, okay, to flow, right? So for that reason, it means current is divided. So it's divided. Hence, we're saying that a parallel circuit is a current divider, and what is going to remain constant in this case is the voltage, because it's a parallel circuit, right? The follow-up question says, calculate the resistance of this circuit. Calculate the resistance of this circuit. Right. I'll give you a further minute to try that. Remember, we're talking equivalent resistance in this case, that we want to replace the 3 resistors with 1 resistor. What will be its magnitude without changing anything in this circuit? Right. Let's go for it. A minute, guys. Right, let's quickly look at it, the feedback for this segment of the question. We want to calculate what is called the total resistance, or the effective resistance of this circuit. So there are 3 circuits, so 3 resistors or light bulbs that are connected in parallel. So we know that for a parallel circuit, we've got 1 over R parallel, okay, which is equals to 1 over R1 plus 1 over R2. Okay, because there are 3 of them, 1 over R3. If there were 4, it would be, and so forth, right? Now, in this case, let's call this R1, and let's call this one, or let's call this R1, this R2, and this is R3, right? Okay, so now we are going to substitute directly into the equation, which says 1 over R parallel, which is what we're looking for, right? Which is 1 over 2 plus 1 over 4 plus 1 over 6, right? Okay, so I'd rather prefer that we simplify the right-hand side, which would obviously give us something of this sort, right? Okay, it means it's better to use this one, which is 1 over 2, okay, plus another one, which is 1 over 4, okay, right, plus fraction 1 over 6, okay, 1 over 6. This gives us 11 over 12, 11 over 12. But remember, we are not looking for the reciprocal of 1 over parallel. We're looking for R parallel. So we could cross multiply there and get RP, okay, is equals to 12 over 11. 12 over 11 ohms, right? Or you could, if you like, you could simplify it into a fraction, which is which is same as 0.92 ohms. Always leave your answer to 2 decimal places, so that remember, you're going to use the same value maybe in further calculations. So it's very important for us to round off to 2 decimal places, right? That said, now we're still on the same circuit. Now they say calculate the ammeter reading on A1. Now you need to be very careful as far as this is concerned. A1 is the current that is flowing through that resistor. So I'm going to give you another minute to try that, and then we'll quickly wrap it up. Let's go for it. A minute again. Welcome back, guys. Hopefully you have made your attempt on the question. Let's look at the current that is passing through A1, and I want to think of A1 as a total in this case. Very, very important, because all the current will pass through A1. So in other words, we're saying that total current from the Ohm's law will be equals to total voltage divided by the total resistance, which is our equivalent resistance that we calculated in the previous question. Right, so the total voltage in this case is given to us as 3 volts, right? It's 3 volts. Let's confirm that. Yes, the EMF, let's say it's the terminal potential difference, okay? Right, which then our total current. So this is the Ohm's law, okay? Let's recall that this is the Ohm's law. Because these are ohmic conductors. So these are Ohm's law, right? So what that says to us that I total, take note of the subscripts, is total, okay? So this is going to be 3 divided by 12 over 11, okay? 12 over 11, in this case, we say it's 0.92. That's the total resistance in the entire circuit. So if we go to our calculator, I total will give us, right? Very important to always round off at the last part of the calculations. So in this case, it's going to be 3 divided by, we can say 12 divided by 11. Okay, it's 12. Okay, 12 divided by 11, which is 0.92, right, closed bracket. Then it means then if we change that to 2 decimal, total current is 3.26 amperes. Very important to indicate the units as far as the current is concerned. So this is the total current that is going to pass through current 1, which is ammeter 1. Ammeter, remember, is connected at a point. It measures the quantity of charge that passes through a point per unit time or per second. That says we shall take our last break, and then after the short recess, we'll come back again and look at further questions in terms of the calculations of circuits. Hopefully you're having a splendid time. See you after the break, guys. Welcome back, guys, after our short break. Hopefully we're still having a good time as far as circuits. It can get a little bit, a lot of calculations, but at the end of the day, it boils down to the Ohm's law and understanding whether it's a series circuit, current remains constant, V is divided. Whereas if it's a parallel circuit, then we know that voltage across the parallel combination is constant, yet current is divided again proportionally. Right, so the question says what? I want to put an emphasis on the word what, in the sense that usually these questions said it's 1 mark. It tests your understanding in terms of classification, because this is a parallel circuit, and then we're talking about potential difference, which is PD, right? And we know that in a parallel circuit, voltage is constant, okay? So because voltage is constant, it means if we can connect a voltmeter across the 6 ohm resistor there, okay, and call it V4, okay, because it's A4 there, right, it will be the same as the value at the top, which is 3 ohms. So it means V is equals to 3 volts, in this case 3.0 volts. Very, very important, right, okay. Now, that said, if we can go a step further with that understanding that voltage is constant, and we want to understand through which resistor will the greatest, emphasis there, greatest, it means this is the most current or the highest current. This is what how you can think of. Right, that said, we want to also substantiate that. So we know that in a typical parallel circuit, this is what actually happens as far as current. The higher the resistance in that path, the lesser the current. So they're inversely proportional. In other words, as the resistance gets bigger in a parallel combination, that has an opposite effect on current, as long as V remains constant. So we're saying by all means that current is inversely proportional to resistance, provided the voltage, current is directly is inversely proportional to resistance. In other words, the higher the resistance, the lower the current. Okay, then the opposite is true. So through which resistor is the greatest current? So the one with the resistor with the least current, with the least resistance will have the greatest current. So in this case, A2 will record the highest current, right? A2 will record the highest current. It means the resistor, 2 ohm resistor, which is the 2 ohm resistor there, is going to have the greatest magnitude of current. That said, it simply means on the other hand, 6 ohms will have the least or the smallest current. So this is smallest current through the 6 ohm resistor because of that mathematical relationship that exists between current as well as resistance in a parallel circuit. Right, let's go further and check additional problems on the same concept. We're still on the same circuit. Now we want to calculate. Now the word calculate suggests that through, by way of a multi-step problem, we want to determine the magnitude or the size of current or the quantity of charge that passes through a point per second. Right, so this is going to be a multi-step problem in the sense that we want to find current. So let's say the current that goes through A4, current that goes through, let's say this is the 6 ohm resistor, or you can say A4 is equals to the voltage, okay, divided by the resistance. This is the V total in this case. We'll say this resistor of 6 ohms, right? So the current through 6 ohms will be through this resistor, which is 6 ohms. So we have the voltage, which we said is constant by virtue of the fact that we said in this parallel circuit, V remains constant. So our current through the 6 ohm resistor is equals to our V total, which is 3 divided by 6. Right, this gives us a current of through the 6 ohm, okay, which is equals to 0.5 amperes. So this is by all means the lowest current that we'll record in this particular circuit, meaning that if we can maybe put it to the test and check just to verify how much current will pass through the 2 ohm resistor. So current through the 2 ohm resistor is equals to V total, which is the constant voltage in the parallel combination, divided by, in this case, we've got the resistance of the 2 ohm resistor, which is exactly 2 ohms. So current through that will be 3 divided by 2. In this case, our current through the 2 ohm resistor, right, 2 ohm, in this case will be 1.5 amperes. Now, we need not exactly calculate the current in the A3 or the 4 ohm because we know it is less than 1.5 but greater than 0.5, right? So we only compared the two extremes. Very, very important. And also, it takes us back to the Ohm's law. We're simply manipulating the Ohm's law in this case because we've been looking at current. In the other case, we're looking at voltage. So it takes us back to the same understanding, right? Okay, now I'll give you a chance, learners, just to attempt the current through A3, okay, with the understanding that we have. I'll give you a minute just for that to check if there's that conceptual understanding. Right, let's go for it, guys. Just a minute for that, then we shall try and consolidate it. Okay. All right, guys, hopefully we've made an attempt on the problem. In this case, we wanted to put more emphasis on the current that is divided, because this is practically your parallel circuit, because V remains constant and current is divided proportionally. The higher the resistance, the lesser the current. The lower the resistance, the higher the current. However, the total current that flows through A1, A2, and it means a current in A1, okay, the reading on A1, all right, that's A1, must be equal to A2 plus A3 plus A4, because this is a typical parallel circuit, because current is divided. It's divided proportionally. So we go back to the Ohm's law. Current through A3, which is 4 ohms. Okay, the notation is not very particular. You can use A3 or you can use 4 ohms, because whatever charges pass through 4 ohm per second is the same that is recorded or registered by A3. So it's our V total, which is constant, divided by the R of the 4 ohms. Okay, in this case, we've got 3 divided by 4, right? So 3 divided by 4, in this case, we have 0.75, okay, 0.75 amperes, which is less than 1.5 and greater than 0.5. So the current through a 4 ohm is exactly that. Surely the conceptual understanding there, I think, is clear for now. It's a matter of checking and pay careful attention to the detail of the question. Right. Now, that said, let's move on to the next problem, which says to us, it continues on the same circuit. What will happen? Okay, now we are predicting. This is a skill, very important skill in science. Now we are predicting what exactly will unfold, or what would happen if the reading on A1 or to the reading on A1. Okay, that's A1. Okay, and A1 is total current, right? Okay, on A1, if the 2 ohm light bulb blows, if it blows, it means this part of the circuit does not exist. Now we are left with the 4 and the 6 ohm. Right. Now, if we can start by looking at what will happen to the equivalent resistance, your R total, because still the 4 and the 6 ohms provide the only 2 alternative paths for current to flow. So the total, or the equivalent or combined resistance, will be in this case 1/4 plus 1/6. Very important for us to understand that if one resistor in parallel is eliminated, what will happen to the total resistance? Okay, so it's 1/4, okay, plus 1/6. Right. I want us to pay careful attention to what will happen to the total resistance. Right. This is 5/12. But remember, we're not looking for the reciprocal. We are saying that 1/R total is equals to, okay, just to go back to that, it's, okay, I'll put it there. Okay, it's 5/12. 5/12. In other words, R total, if you do your maths, it will be 12/5. 12/5 ohms. Okay, 12/5. Okay, I'll do 12 divided by 5, which is equals to, right, is the 2.4. So R total now is 2.4 ohms. Right. Now, because R total now is 2.4, now you'd understand that the total resistance, R total, has increased. Right? So the effective resistance in this circuit has increased. So what effect does that have on the total current? Therefore, total current will decrease, right? Total current is definitely going to decrease, because we said that the relationship that exists between current and resistance is that they are inversely proportional. Because why? Current and resistance are inversely proportional, provided that the voltage remains constant in a parallel combination. Very, very important. Right. Now, I'll quickly want to go through this context of this problem just to consolidate one or two ideas as far as electric circuits are concerned. Right. The potential difference, which is the voltage across each of these batteries, is the same. So same voltage, okay? Whatever voltage is in each of these three circuits is the same, okay? Now, in which circuit are bulbs burning with the same brightness? Same brightness. Obviously, we would want to look at these circuits very carefully, right? We understand that this one, if this the resistance in this one is R1, okay? The resistance in this one is R2, right? Okay, and then the resistance in this one is less than the total resistance in each of these because it's a parallel. So, but here, because this is, let's call this circuit C, let's call this B, and let's refer to this one as A, sorry. Right, is A. So you'd realize that in the first circuit, these bulbs are connected in series. Because this is a series circuit, the amount of charge that passes through is the same. So current is constant because this is a series circuit. So the bulbs in circuit C are going to burn with the same brightness. Brightness has an implication on the amount of current. Very, very important. Right. That said, it says here the potential difference is the same. It's still the same circuit. The resistance of the bulbs are the same. So these are what we call identical bulbs. These are called identical bulbs, which have got the same resistance. So which one of these will burn the dimmest in the circuit? Now, if you check, this one is got, we say it's R1. This one will be, let's say, okay, let's call this. Let's call the resistance R because it's only one resistor there, the light bulb, and this one will be 2R. And this one will have the lowest resistance between the three because it's a parallel combination. So the one that is dimmest has the lowest current, okay, low current. So in this case, the one that has got the lowest current is the one that has got the highest resistance. In this case, obviously, circuit C has the highest resistance because we said I is inversely proportional to resistance, right? So the higher the effective resistance of a circuit, the lower the current, right? That said, I think it brings us to yet another end of yet another exciting session of Grade 10 Physical Sciences, which is based on calculations on circuit problems. But the conceptual understanding of current, resistance, as well as potential difference becomes very, very important. So at the end of the day, after all has been said and done, what is it that we take home today? We must understand that there's a series and a parallel circuit, but then in a series, as far as current is concerned, it's constant because the same amount or quantity of charge passes through a point per second, yet voltage is going to be divided in that particular circuit, whereas the higher the resistance of a resistor in a series circuit, the greater the potential difference across, which explains why, again, we connect the voltmeter in between 2 points in parallel, as well as the ammeter in series at a point. Right. This brings us to the end of our session. From myself, Themba Ncube. Let's hope we had an exciting session. Hope to see you next time again in our next session on practice on revision on term 1 work, term 2 work, just to prepare for the June exam. Cheers and goodbye for now.